Question starts out so nicely trying to understand what's going on. We've just got discs in the bag. That's all. We're drawing discs from the bag. They're the same color, then they're put back in. This is where it suddenly starts to step up a bit. If the discs are different colors, they are removed from the bag and the disc of the third color is placed in the bag. Okay, that's a bit different to normal. And then the point is that we just keep doing this until there's only one disc left in the bag, or there's just like some of the same type. And then we're asked, what is the color left in the bag? Which actually is a bit of a hint, really, in this question, because I don't know, when you first look at this question, you sort of might think that actually it's going to depend which ones you pick. Question's basically implying, it doesn't say color or colors are possible. The question seems to be implying that there's just going to be one color that's found. So a good starting point is to follow a process to work out what that color might be, and then we can maybe make an argument towards it. That's my advice anyway. I don't think I couldn't just look at this and like know straight away what to do. And the hardest bit of this question is like making a good argument for why it's the certain color that we're going to find. So let's start out with 7, 8, and 9. And I think I'm not going to like write this down clearly about what I'm doing. I'm kind of explaining it, but I think it would be advisable to make good explanation along the way of what you're doing. So I'm going to take um, all the blues. I'm going to take a blue and yellow out at the same time, but I'm going to do that 8 times. So if I do that, then I'm going to take all the blues out and I'm going to take 8 of the yellows out. And then remember, it says if we do that, then we have to put in the third color. So we'd actually put in 8 reds and get up to 15. Okay, so I'm just kind of messing about with the process. I'm definitely going down in um, in discs over time. So now we can kind of then follow the next procedure. So now I'm going to remove a red and a yellow. Okay, I can't take a blue one, have to take a red at this point. So that would take me to 14 and 0, and then actually we're going to go up by 1 here. And then I'm going to take a red and blue. So I'm going to go down to 13, take this one and go up by 1 here. And we can very quickly see that there's a pattern forming. Whenever it's odd, whenever number of red discs is odd, we're going to have a yellow disc. And when it's even, we're going to have a blue disc. So I can kind of just extrapolate, I guess, as such, just argue that I can follow this on the same way. And so let's go down to 3 discs. It would still then be 3, 0, 1, and take it from here. So now I'm going to take a red and yellow. I've maybe write a few more words just to explain what I've done here, but like I said, I'm just kind of outlining a solution more than anything. Um, so now I'm going to take a red and a yellow. So this will be 2, 1, 0, and then it'll be red and blue. So 1, 0, 1. Okay, so we're left with those two. So I've got to now get red and yellow again. And you might be able to spot right from here that that was kind of going to happen, but I just wanted to put a few more steps in. So then I'm going to go 0, 0, and 1. And there it is. I seem to be left with a blue. And that might be enough for you to think, oh, I can make an argument based on that. Me personally, I thought, you know what, I just want to check, like, is that necessarily going to happen? I mean, it kind of implies that it is, but I just wanted to have another look through it. So I started up again. Red, blue, yellow, 7, 8, 9. And then this time I thought, all right, I'm going to take the reds and the blues out, first of all. And what did I write here? I'm going to do it 7 times. So this will become 0. This will become 1. And then I'm going to get 7 more yellows. So this will become 16. So slightly different setup, but similar process happening, you can see. So now blue and yellow. So it'll be 0, 15, and 1. And it'll be red and yellow, 0, 1, 14. And we can see if we follow it down, we're going to again get all the way to, if I take away, sorry, why am I writing 3? I'm going to get 1, 0, 3, okay, because it's always odd when it's yellow's odd when red is 1. So then I'm going to get 0, 1, 2, 1, 0, 1. And again, we're going to get blue by itself. So get some credit for that, but that's not going to get you much because really the focus of the question is what color is the disc and like how can we know for sure? Just because I've done 2 examples, that is not conclusive at all. So I suspect, not get much credit for this, but having said that it's a good starting point. And there's one more thing that this process kind of gives you. It kind of tells you like a bit of a, if you look at it a bit more, you can maybe start to see certain things happening. For example, when red is 15 here, we have yellow as 1. Look, they're both odd at the same time. Um, Now, when yellow becomes even, 0, then red becomes even. So they seem to have the same, we call it parity. They have the same, they're both even at the same time. They both have the opposite to blue. And let's look at the second time I did it. It seems to be happening again. So that can actually be our focus. So explanation, I suppose, or solution. This is going to be our basis of our solution. Okay, this is quite tough to see in my opinion. Hopefully as I'm explaining it, it'll make sense. And if, as you do future problems, it's like certain ways to solve certain problems. Like sometimes you draw a chessboard to make things work, show that you can't use every move or whatever. This using parity is another kind of technique to become familiar with. So we started out with 7, 8, 9. The main thing is that we had odd, even, odd. So red, blue, if those two are taken out, gives us even. Actually, I will write the numbers. No, I'm going to work generally now. So clearly it's going to become even, odd, even. Okay, that's from that starting point. So I should maybe just say that. If I instead did red, yellow, then I'm going to get even, odd, even. Same thing's going to happen. And that just leaves me. I remember sorry, I've not actually said this at any point, but I am completely ignoring if I get 2 of the same color because if I do that, I just start again. So I might even write that. Ignore picks of same color because it just doesn't matter. It's like they don't happen because we put them back in and we do it again. So we can just reject that. So I definitely don't need to look at that here. So then I've left with blue and yellow. This time I would subtract 1 from the blue and yellow and add 1 to the red. But again, I'm going to get even, odd, even. So any drawing of 2 different colors changes the parity of all three numbers of counters. And another draw, I don't know if I should really need to argue this, another draw will change it back. So basically going to alternate And that's something that kind of comes out of here. You don't necessarily see it, but we are alternating the parity. Odd, odd, even, odd, even, and so on. And so if we have for even, one thing I've not said is that red and yellow have the same parity. Should probably say that. So they're either both odd or they're both even. Okay, so let's look at this situation. Actually, sorry, that's the second situation I want to look at. The game cannot end for this one because we only stop when we've got one single color. We'll have more than one color. Obviously, they're all positive numbers or zero. They can't be negative. So the game will end here. And our number of counters are we equal the number of number of red counters will equal the number of yellow counters will equal 0 and b will equal 1. And the two above examples show possible games where this happens. So there's two parts to this question. First of all, it was like just a bit of motivation, we call it, just playing around with the game, seeing what happens. In both cases, I found out that we were left with a blue counter. The second, and by far the hardest part, is to kind of construct an argument why this must always happen. In this case, I'm looked at the parity of the number of counters for each, argued that it changes every time. Hopefully, my argument is deemed sufficient. Said that we can't finish the game on this one because we'd have more than one counter of different colors. So it has to end here, okay? Because those are the only two states, and it makes sense that it ends here when R is 0, Y is 0, and B is 1. Referred back to my examples. So that's pretty good. I think I could maybe fill it out more. And obviously, my advice would always be to have a look at the official solutions. They sometimes like are quite scant in, how like you might look at them and think, how on earth did they even know to do that? But what I'm trying to do in this video, obviously, is just show where you might get that idea from, um, and realize that it's parity. So well done. Good, interesting, but tough question here, and a nice challenge overall. Thank you.